Hello everyone, today I am going to explain about pipeline hazard. In computers, pipelining is used to execute multiple instructions faster, but sometimes problems occur that slow down this process. So this problem is called pipeline hazard. So in this presentation, we will understand what these hazards are, why they happen, and how to solve them. So before understanding hazards, we need to know what is pipelining. So pipelining is a technique used to increase the speed of execution. Instead of executing one instruction at a time, multiple instructions are processed simultaneously. So it is like assembly line in a factory. Different stages work at a time at the same time so the work finishes faster. So pipelining improves the performance by doing many tasks in parallel. So simply, pipelining means executing a multiple instruction at the same time in different stages to increase speed. Even though pipelining increased speed, sometimes problem may occur. These problems are called pipeline hazard. They prevent the next instruction from executing properly. Because of this, pipeline may slow down or stop temporarily. So, pipeline hazards are obstacles that reduce the efficiency of pipelining. Let's see the small example of it. It's like a traffic jam in a road, vehicles cannot move smoothly. So, pipelining hazards are problems that disturb the smooth execution of the instruction in pipelining. There are three main types of a pipelining hazard. First is a data hazard, and next structural hazard, and next control hazard. In data hazard occurs when one instruction depends on the result of another. So the data is not ready yet. And the structural hazard occurs when hardware resources are not enough. Two instructions try to use the same hardware at the same time. So in control hazard occurs due to the branch or a jump instruction. The instruction is not known immediately. So pipelining hazard are classified into a structural, data, and a control hazard. So data hazard is also known as a dependency problem. Here, one instruction needs data from a previous instruction, but the data is not ready yet. Why it occurs? The result is produced later in write back WB stage, but the next instruction needed earlier in a execute EX stage. So there is a timing mismatch. So in clearly data hazard occurs because the required data is not available at the correct time. It's like waiting for a result before continuing the next step. Here let's see the types of data hazard. Data hazards are of three types. First one is raw, which means read after write. This is the most common type. An instruction tries to read data before it is written. So next type is WAR, which means write after read. Here an instruction writes data before another instruction needs it. Next type is WAW, which means write after write. Here two instructions try to write to the same location. So among this, raw hazard is the most important in the pipelining. Let's see an example of raw hazard. Here we have a instruction 1 where sub x2, x1 and x3. It computes value of a x2, and in instruction 2 where we have and x4, x2 and x5. Here it needs the value of the x2. The second instruction needs x2, but the first instruction has not written x2 yet, so the second instruction must wait. This delay is called an raw data hazard. So raw data hazard occurs when an instruction tries to read a data before the previous instruction writes it. Let's see how to solve the data hazard. We use a technique called forward bypassing. In forwarding, data is taken directly from the pipeline stages. It is sent to the ALU without waiting for write back stage. So here data is forwarded from the stages like EX or MEM likewise. So the next instruction can use the data immediately. It works for ALU operation because the result available earlier. It have a limitation like it does not work for a load instruction followed immediately by user because data is not ready in time. So forwarding reduces the delay by sending data directly, but it has some limitation. So finally, forwarding sends data directly from your pipeline stages to avoid waiting, but it does not work for load use cases. Here, we use stalling when the forwarding fails. Here, when forwarding cannot solve the problem, we use stalling. Take the example. Here we have LWX1 and 0 of x2. This loads the data from a memory, and the instruction 2 we have add x3, x1 and x4. Here it needs x1. So the data from the memory is not ready yet immediately. So the next instruction cannot use it. To solve it, we insert a one stall or a NOP, no operation. NOP means the no operation. This gives a time for data to be ready. After that, forwarding can be used. Here we have a hazard detection unit which checks this is a ID stage. It sees if it is a load instruction and if the next instruction uses the same register. So stalling passes the pipeline temporarily until the data is ready. To summarize this, here data hazard which causes the dependency between the instruction and the solution is forwarding and stalling. In structural hazard, it causes inefficient hardware resources. So the solution is using a more hardware like separate memories. And next is a control hazard. It causes a branch instruction. So the solution is stalling and a branch prediction. So finally, the pipeline hazard reduces the performance and we can handle them using a proper technique. So these are the three hazards and their solution. Thank you.